leaving this leaf in whatever form. And the major sources of energy for a leaf are shorter wavelength energy from sunlight and longer wavelength energy, say, from the sky and the surroundings. The major uses of energy by this leaf are either evaporating water or heating itself up relative to its surroundings. So latent heat flux, sensible heat flux. And those have to match. So we can use that. And if I remember, I showed you this stuff from Dave Woody a long time ago, where he looked at the difference between real grass canopy and this fake grass on the inside of the football stadium. And found that, sure enough, the real grass was 35 C, the fake grass was 65 C at about the same time of day, right? Because this plastic doesn't evaporate water like the real grass does. So because this can't evaporate water, it's got to heat itself up to get rid of all that energy it's absorbing. That's what I mean by this energy balance. Yeah, I think I just said all this. So let's keep that in mind as we struggle through this, as I struggle through explaining this. Great. Okay. So just some background about radiation. The parts of the spectrum that we're going to be interested in for this are range from ultraviolet through, that's less than 0.4 microns, so less than 400 nanometers wavelengths, through the photosynthetically active band, 0.4 to 0.7 micron wavelengths, into the infrared, the near infrared, or the close range, close to the visible, and then the farther infrared, including way out here in the thermal part of the spectrum. All right. Okay. And the so-called optical properties of the leaves vary throughout this range of wavelengths. So how they interact with the leaf depends on what wavelength. Solar radiation typically is about half PAR and half near infrared. So if you have a pyranometer that measures solar radiation and compare it to a quantum sensor that measures PAR, typically one will be about half the other one. About half the solar is in PAR. And thermal radiation from the sky, 15 degrees cooler than the air. Okay. Okay, so the leaf optical properties depend on what wavelength you're talking about. Here are some numbers from, well, here's some rough approximations. Right? The reflectance from a leaf is about 0.1, 10% in the visible part of the spectrum, and about 0.4, a lot higher, in the near infrared part of the spectrum. So leaves absorb most of the visible light, but I'm getting ahead of myself. Okay, that's the reflectance. The transmittance, you see the numbers about the same. The absorptance, so in the PAR is 0.8, which would be a low, in fact, a low value. These are very rough approximations. But in the NIR, it's 0.2. So most of the near infrared radiation either is reflected from the leaf or transmitted through the leaf. Most of the PAR, the photosynthetically active radiation, is absorbed by the leaf because that's what it uses for photosynthesis. And the thermal, you see here, emissivity, perfect black body is 1, and the leaf maybe 0.95. So it's almost, it's sometimes they call it gray body. Anyway, here's a graph that shows the radiation reflected from a leaf from, that's about 400 nanometers to 2500 nanometers. So here's the visible part of the spectrum. Here's the near infrared part, and then here's the middle, or sometimes it's called shortwave infrared part of the spectrum. this dip here and this dip here are due to absorption by water molecules in the leaf. So those reflect, those features show up like this. The transmittance on this scale, starting from 0 up here, is given by this. And so the absorption is the difference between these two. And you can see how that goes. But all this energy that's absorbed by the leaf has to do something. Here are some reflectances that Betty measured over the summer. And you can see these are real data. These are made up approximations. You can see how those vary. So the leaf optical properties are something that are here are the leaf optical properties in red compared to the canopy, similar canopy properties. And in this case, the fraction of PAR that's absorbed by the canopy is called F. So here's the PAR that's absorbed by the leaf, this big part of the spectrum. But when you go to a whole canopy, that's shown in blue. This is the PAR that's absorbed by a canopy over the course of a growing season. And here's maize, and some more maize. Without getting into a lot of details, the canopy absorption is related to the canopy architecture, the leaf area index, how much leaf area is in the canopy, and the distribution of those leaves in the canopy, leaf angle distribution. But let's leave it there. Okay, anyway, let's go back to leaf energy balance, and starting first with leaf radiation balance. So the net radiation absorbed by the leaf, net radiation absorbed by the leaf is the incoming, what's incident on the leaf, minus the outgoing, which is the thermal radiation. Everything emits radiation based on its temperature. And for a leaf, this is Stefan Boltzmann law, where the amount of energy is sigma t to the 4th times the emissivity. So that's leaf temperature to the 4th times Stefan Boltzmann constant times emissivity times 2, because there's 2 sides to the leaf. So this is the outgoing long wave, because the leaf is at such a temperature that that energy is in longer wavelength. And this is the incoming net radiation of all the wavelengths. This is all the wavelengths too, but it's all long wave because it's a relatively cool temperature compared to something like the sun. Okay, all right. So this is Stefan Boltzmann law, and this is the leaf radiation balance, the net radiation absorbed by the leaf, incoming minus outgoing. Now, leaf energy balance, how is that radiation absorbed by the leaf used by the leaf? Okay, well, that net radiation is split into H plus lambda E, the sensible heat flux plus the latent heat flux, plus storage plus photosynthesis plus some minor things. H is the sensible heat flux based on the difference in temperature between the leaf and its surrounding. Lambda E is the latent heat flux by evaporating water, and we just saw Penman-Monteith equation. It's one way of expressing that. Storage term is due to changes in temperature within the leaf itself. So as the leaf temperature changes, some of that energy is stored in the leaf, and that's that term. That's a small value and usually neglected. Photosynthesis, some of the energy is used actually for photochemistry, right? That's the whole point of being a plant, right? That's a small amount of energy too. and usually it's ignored, on the order of 1%. Imagine that, all the energy falling on that leaf, only 1% used for this. Okay, take over. Yeah. Okay, so usually storage and photosynthesis term are neglected. And remember, the net radiation absorbed by the leaf is the incident minus the outgoing. And we can then neglect these terms and rearrange this equation to write the leaf energy balance as the latent heat flux plus the sensible heat flux plus twice this emissivity term, the long wave thermal radiation emitted. Now what I want to do is give you an equation for this. Here's this equation. These equations will have the leaf temperature in them. And then we'll come up with this monster equation and we'll rearrange it to solve it for tea leaf. I think I will get it. So let's consider the sensible heat flux term. These are in energy, watts per square. Sensible heat flux, 2 rho Cp Gb times the difference in temperature between the leaf and the air. All right, so this is driving that latent heat flux, this difference in temperature. And here we've got some proportionality things. And the 2 is because the leaf has 2 circles. Gb is the boundary layer conductance for the leaf. Right? It's that layer of still air next to the leaf. And since this is a heat flux, we don't have to worry about the stomata at all. They're not part of the problem. That energy is being lost from the surface of the leaf, not from the inside of the leaf, from the surface. And so we just put these things in here. And there you go. There's the equation for sensible heat flux in energy. What do we have to do to solve this equation? Well, we have to know something about the boundary layer conductance. Remember, that's based on the dimensions of the leaf length, and really based on the wind speed over the leaf affects that. But we can come up with estimates for that. Cp is more or less of a constant, specific heat of dry air, constant pressure. Rho is density of dry air. Okay, so all these terms, T air we measure with the thermometer. The leaf temperature is the thing that is unknown typically for this equation. And what I'm proposing to do is tease this value out of our big equation at the end and solve. Latent heat flux is a little more complicated. Here's the latent heat flux from a leaf written in terms of driving force being the difference in absolute humidity between the inside of the leaf and the outside of the leaf. You know relative humidity, right? 0, super dry, 100%, in the sauna. Relative humidity. But absolute humidity is grams of water vapor per meter cubed of air. So how much, on a mass basis, how much water vapor is there in a given volume of air? That's called the absolute humidity. The relative humidity varies over the course of a day a lot, or it can. The absolute humidity is much more constant over the course of a day. Okay. Anyway, that difference in absolute humidity between inside of the leaf, which is at the leaf temperature, and the outside of the leaf is the driving force that moves water out of the leaf, or we can use that as the driving force. And here now we have the total leaf conductance for water vapor. That total leaf conductance, remember, includes the stomatal conductance and the boundary layer. And the parallel combination of both leaf surfaces in the case of emphystemes. All right, so there it is. If you're more conversant in vapor pressures, we can rearrange this equation in terms of difference in vapor pressure, and this is how typically, I've been doing it with sometimes this P pulled over here and written as a delta W if it's a mole fraction. So this should be not unfamiliar. But again, the total leaf conductance for water vapor is an important consideration. Lambda is the latent heat of vaporization for water. Rho is the density of dry air. M is the ratio of the molecular weight of water vapor to that of air. And, you know, it's a simple equation. All right? So now we have the following equation for leaf energy bucket, where Rn prime H plus lambda E plus the emissivity term. And here we have Rn prime is this. Here's H. Here's lambda E in terms of vapor pressure. And here's the emissivity term. Now, if we're interested in the leaf temperature, all we have to do is solve this equation for T leaf and measure everything else. Easy. This is a picture of how leaf temperature varies over the surface of the leaf. Look at that. It's not uniform, right? We won't get into this kind of detail. All right, so how do we solve that for T leaf? Has anybody taken numerical analysis? No? I took numerical analysis. This is one of my favorite classes. Right? What is numerical analysis? Well, numerical analysis. You all use computer, right? You use a computer. A computer just deals in zeros and ones. Computer doesn't know what pi is, right? That's not a rational number. You can't express that in a string of zeros and ones. All you can do is approximate. How well do you have to approximate pi to use it in the equation to get an answer? That's the kind of thing numerical analysis is. When I took numerical analysis, all of these many years ago, the person I took it from said, and I don't know if this is true or not, I mean, I'm not a computer science. All of numerical analysis boils down to the Taylor series. So, you've all had calculus, right? You remember Taylor series? Mm-hmm. That's how we're going to solve this equation. Okay, so this is a monster, right? It's got T to the fourth in it. It's got this saturation vapor pressure dependence on the leaf. Here's a linear thing, that's easy. But what we're going to do is linearize these things by using the Taylor series approximation. Okay, what is Taylor series? Taylor series is a way to approximate a function based on the information you have at some other, approximate a function somewhere based on information you have where you are, right? And so f of x is the function we're trying to approximate. The Taylor series says that's f evaluated at some point a, that's not on it, plus how far away x is from a times the first derivative, plus how far away x is from a squared over 2 factorial times the second derivative, and so on, third, fourth, nth derivative. It's an infinite series. So this infinite series can be used to approximate this function as closely as we would like. So what we need to do is linearize this equation in terms of T leaf, or in terms of delta T, where delta T is T leaf minus T air. Same thing. The sensible heat flux term's already linear, right, as I said. T leaf minus T air, so that's easy. We don't have to do it. The outgoing long wave term, so this 2 epsilon sigma T leaf to the fourth. Since we don't know what T leaf is, we evaluate that at the air temperature. We don't know what the function is at x, but we know what it is at A, the air temperature, times the first derivative of this function. So the first derivative of T air for T air cubed times delta T times the rest of this stuff. So this approximation is just the first two terms of the Taylor series. So 2 epsilon sigma T leaf to the fourth is about equal to 2 epsilon leaf sigma T air to the fourth plus this other part of the term, the first derivative, evaluated at the air temperature. Right? Now, this equation is linear in T leaf. We can do the same thing with the saturation, the slope of the saturation vapor pressure curve. Again, we don't know what T leaf is, but we know what T air is. We can evaluate the saturation vapor pressure at the air temperature. Right, that's right here. And then add this next term of the series, the derivative, the first derivative, which is S, giving us S at T air is the slope of the saturation vapor pressure versus temperature curve. Evaluate at the air temperature times the rest of this stuff. So we're only taking the first two terms of this Taylor series approximation. You know, it's a rough approximation, but what it allows us to do is linearize this equation in terms of T leaf. And then there we have it. This is the stuff that I just went into. We can solve this equation for delta T, and it's this monster. Right? So here we have delta T, or T leaf on this side, and everything else on this side that doesn't have T leaf. And this is the way that we can estimate the leaf temperature of leaves in the cube. In terms of variables that can be measured, we can easily measure air temperature, easily measure pressure. Some of these are constants. We can get at the boundary layer term, because knowing dimensions of a leaf and wind speed profiles through the canopy and things like that. So we can this side of the equation is usable. And then we can estimate a leaf temperature from this. All right, I don't expect you to remember how to do this or even what the Taylor series is, although it's all of numerical analysis. What I expect to stick in your head from all this is the key role that stomatal conductance plays in this whole system. Right, so here we have the total leaf conductance for water vapor, total leaf conductance for water vapor. Stomatal conductance is implicit in these terms, right? And so if the stomata are open or closed, it has a huge effect on the value of this delta T, the difference between the leaf and the air temperature. Huge value, huge role to play in that. In fact, it's the single most important factor that governs the leaf temperature. Well, it's single most, well, a couple of factors, right? The air temperature has a big effect on it, right? But the stomatal conductance has also a big effect. The plant can't control the air temperature. The plant can't control its stomatal conductance. How? By changing the osmotic potential in the guard cells. Yes. And there you have it. That's the key role that's played by stomatal conductance in this equation. Stomata are, how do I say it? Stomata are critical determinants of the leaf energy budget, and hence the leaf to air temperature difference. In other words, the temperature of leaf depends on what the stomata are doing. Or another way to look at it is the value of delta T can be used to infer something about the stomatal conductance. And that's what this guy was doing. Or that's what the people in this is just a picture of somebody out in the field. I don't know if this is even a person that's on this paper, but that's what they were doing in this paper, is using properties of the canopy to infer what the stomata are doing. For a while, I don't know, there was a company that made essentially an infrared thermometer that they called an irrigation scheduler. Right? You go out and point it at your canopy, and once it reached a critical value, it will tell you, oh, you better irrigate. And that's based on this type of analysis. I don't know if that makes. Okay. So once we calculate the temperatures of leaves and canopies, we can quantify effects of temperature on properties, like we can calculate vapor pressures then for leaves in the canopy. We can look at this leaf to air vapor pressure difference and how that affects stomatal conductance, and use that in our model of the plant canopy. We can use the Farquhar-Van-Kameren model for C3 photosynthesis, along with this Ball-Woodrow berry for stomatal conductance, the equation I gave you a few days ago, to look at stomatal conductance. And you can come up with, and these are the two, you can come up with a way to estimate what's going on in the entire plant canopy based on knowledge of stomatal conductance and a bunch of physical properties. And if you look at this website here at Wisconsin, let's see if it works. You can access, yes, here it is. You can access this model, which is a detailed representation of the plant canopy based on all the stuff we've been talking about. That takes the physical conditions above the canopy, the physical conditions below the root zone, and calculates everything in between based on what the plants are doing. So, and that can be used to estimate photosynthetic rates, transpiration rates, what have you. So it's a comprehensive soil plant atmosphere model, right? Based on these properties. This one's called Cupid. There's another one. Another one. Hydrocomplexity. So here's another one that's a similar approach. Schematic of the canopy, root, and soil system model. So it's a similar microclimate type model that allows you to predict what's happening with the vegetation here in the canopy, to look at things like water use and CO2 uptake. This one, it looks a little bit different now. This was here, so again, you can look here. I don't know if you can get the code for keeping. You can download the code and actually play around with it. I don't know the details of this hydrocomplexity, but very useful an approach to estimate what's going on in plant canopy. And my question to you is, okay, here's the surface of the earth. We know that stomata are important in partitioning energy on a canopy scale. What about the global scale? What role does stomata play in this global partitioning of energy and CO2 and radiatively important gases like methane? So I leave that as an exercise for the reader. Questions? That's a bad sign when there's no question. I interpret it as a bad sign. Okay, well, think about this stuff and let me know when you have questions. Right? Plants are really important. You know, I was I was lucky enough to do a part of a year postdoc right after I finished my PhD here at Nebraska. And it was a NASA project in Kansas at Konza Prairie, and it was called FIFE, the first Izzleskip field experiment. Izzleskip stood for something. Anyway, the people I was with from Nebraska, mainly John Norman and Blaine Blatt, Betty was involved, Shashi was involved. We were the only people that made plant measurements. And they were looking at energy partitioning and interaction between the Earth's surface. This was a NASA, primarily NASA-funded project, looking at interaction between Earth's surface and the atmosphere. You know, exchange of water vapor, exchange of CO2, exchange of energy. And we were the only group out of that big project that was looking at plants, making photosynthesis measurements. John and I were making photosynthesis to molecule measurements. Okay, fast forward to the next in this big group of NASA projects, because NASA has one of its missions is to observe the Earth, right? It's in space too. It's not just going to the moon or Mars or, you know, Alpha Centauri or something. The Earth is a thing that NASA's interested in. And so they fund a lot of research looking at the Earth. Okay, so after FIFE and this project went on for a few years, there was another project called Boreas. Boreal Ecosystem Atmosphere, I forget what it stands for. But anyway, it was in Canada. And it was looking at the boreal forest and how that interacts with the atmosphere. And there were maybe 80 groups funded for that project, and probably 40 of them were looking at plants. Because at least one of the things that people realized after doing FIFE was, gee, the plants are really important in partitioning the energy and interacting with the atmosphere. They're not just green mush on the surface. They're actually doing stuff. So, you know, give it to Pierre Sellers and Forrest Hall, and Diane Wickland, people like that were funding these projects. They came to that realization that plants are really important. So, again, I leave you with this. What role do plants have in this? Right? That's all I got.
So the equation that we have to measure our leaf temperature?
Yeah.
Or